So when we saw the Lagrange multiplier and the Lagrange method of finding out the optimal in the two or more variable cases, we showed an example wherein we saw how if I want to maximize the utility function in n variables, given that the income is equal to p1 x1 plus dot 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 pn xn, we saw in this example that the value of lambda was basically giving us the marginal utility of money. This lambda was coming out to be nothing but del u, or if I can call it MUI by PI. So how much utility I can get for an extra rupee spent. That is what was coming out to be lambda, which we said is the marginal utility of money. So this was a very small example because we took only one constraint here. Okay. In reality, there can be multiple Lagrange multipliers because we have multiple constraints in front of us, right? Let's consider that example. The generalized example would make, so let's actually put in the objective function that I want to maximize or minimize. Let's call it fx. And now the constraints are multiple, subject to where j is equal to 1, 2, up to m. There are m constraints, okay? And obviously, I'm putting all this in terms of a vector. So this x is supposing x1 to xn. There are n variables in terms of x. And going forward, I'll also consider that C is a vector which is C1 up to Cm, right? C1, C2, C3 up to Cm. So when I solve this, when I put it in terms of a Lagrange, the Lagrange basically would look like this. Fx minus lambda j, gj minus cj. Okay. From here, from the Lagrange of more than two variables, we have already seen that you'll get the result from the first order conditions as, if I differentiate with respect to I, minus lambda j, okay? Or in other words, what you'll basically get is that fi is equal to lambda, this equation, if I can call as star, okay? This will come handy. Now, after solving it completely, you will get the values of x1 star, which will be a function of c1 up to cm. Similarly, xn star will also be a function of c1 to cn. Okay, so you will get each of these values being a function of all the constraints value from the constraint. Okay, all the constant values from the constraint, that is what you will get. Okay, so basically the optimal value of f, that is, if I call it f star, is basically f star x1 star, which is a function of c1 to cn, which I call c. Similarly, xn star, which is a function of c again. Okay, so all in all, basically f star is also a function of c. Okay, this f star is also a function of c, is ultimately a function where c is the vector c1 to cm. All right, now you will notice that here we'll have the generalized result that my objective function optimal value will change with value of ci is changing according to the Lagrange multiplier, okay, which is also a function of c, this I being from 1 to m, because obviously there are m constraints and m Lagrange multipliers, m for Mumbai. Okay, so this is what you will get ultimately. We can actually prove this. We can prove this. You want me to prove it? इसको prove करें? चलो ठीक है, इसको prove करते हैं. df star is nothing but, if I take a look at this entire expression, is d of f star, which is going from x1 up to xn. Basically what I'll get is, I'll get f1, that is, चलो ऐसे लिखते हैं, plus del f star del x2 dx2 del f star del xn dxn. This can be basically written as summation I is equal to 1 to n f I, if I can write it, fi dash dxi. ऐसे लिख सकता हूं. Now from what we had from here, fi is basically lambda j del gj by del xi. Okay, so fi is basically that, right? Okay, basically I'm differentiating with respect to this. This is the, oh sorry, this is summation. I'm sorry, here I missed out the summation. J is equal to 1 to m. There are m constraints. Okay, so this is what each of the fi will be. So basically, what will I write here? J is equal to 1 to m. And what will this be? This would be basically lambda j del gj del xi dxi. Okay, this is what I'll get ultimately. Okay, now this can be simplified further very easily. Just take a look at each of these gj. Now if I differentiate this entirely, I'll get, because for each of them, for each gj is a function of x1 up to, this gj is nothing but x1 up to xn. It's a function of x1 up to xn. Okay, so if I differentiate, I'll get del gj del x1 dx1 plus del gj del x2 dx2. So ultimately it's nothing but the summation. This is very similar to what we had here. Okay, this entire thing can be written as a summation. So this is what I'll get. So del gj del xi dxi is equal to dcj. Okay, so this can be written as j is equal to 1 to m. So it will be lambda j, and summation I is equal to 1 to n. This entire part is nothing but dcj. So very clearly, so df star is nothing but this. So we are able to easily prove the fact that df star del ci is equal to lambda I ci. If I consider for a single value. Okay, so that basically tells us that if I increase the constant value in the constraint by whatever, it affects my optimal f according to the Lagrange multiplier. So this Lagrange multiplier forms a key area when it comes to economic studies, because this basically tells us the movement of the optimal value of f according to changes in the constraint. Okay, and the economic interpretation, when it has come down to a utility function and a budget constraint, is very simple. It's the marginal utility of money. In other examples, it will be something else. But what it basically gives us ultimately is, if I call it in economics, this lambda is nothing but rate at which the optimal value of the objective function changes with respect to the constant. Okay, this can also be said to be the shadow price or the marginal value imputed to a unit of resource, say I. Okay, so it's nothing but the shadow price. It's nothing but the shadow price. And in the case of consumer behavior, it's called the marginal utility of money. Okay, the rate at which optimal value changes given changes. So that is the economic interpretation of this lambda.